I would like to welcome you all to this workshop. I would like to take this opportunity to thank our funders, European Union, Marches Lab, Midlands Ingen, University of Wolverhampton, Hereford Council, and Skyland Park. I would like to now introduce our esteemed speaker, Professor Lindros Maglares. Professor Lindros is the Professor of Cybersecurity in the School of Computer Science and Informatics at De Montfort University. He has been the Director of National Cybersecurity Authority of Greece, and to add to his list of accolades, he has been featured in Stanford University's list of world's top 2% scientists. Before I hand over to Professor Lindros, I would like everyone to know that we will be recording this workshop, so we ask everyone to keep their videos and microphones switched off. If you have any questions, you can add to the chat box, which is on the right of your screen, and Professor Lindros will be looking at these questions and answering them at the end of the session. I will now pass over to Professor Lindros.
Thank you. Thank you for the invitation. Just let me share my screen.
Yeah.
So if you can see, I can start.
Yes, we can see. Thank you.
Good. So thank you again for inviting me to give this lecture today, this talk. So the topic is innovative privacy preservation and authentication mechanisms. I'm going to present two of our novel solutions we have built in the Montfort University in collaboration with other universities and other research centers. This talk is split in two parts. The first part is our novel two-factor honeytoken authentication mechanism. And the second part is our novel secure node end-to-end encryption mechanism. For both of these solutions, I will give you some introductory information. Then I'm going to show you some parts of the solution, and I have some video demonstrations of how they work. Both of them are still work in progress, so you're going to see some prototypes. Okay, so let's start with what are the computer security challenges of nowadays. Everyone knows that the security is not simple. There are a lot of new potential attacks on the security features of any solutions that we provide. So this is something very important. We think that we provide a solution that can improve security of the system, but this solution can also be hackable. Also, the procedures that are used to provide particular services are often counterintuitive. So we don't think about security sometimes when we offer a solution, especially when we try to offer the solution as fast as possible. And it's necessary to decide where and what security mechanism we need to use inside our solution. So any system that we build, any solution we build needs to be monitored all the time to see if there is anything abnormal happening inside the system. And one other thing that we have to have in our mind, that security most of the time is an afterthought. So what security mechanisms can we use? Normally we involve more than a particular and specific argument for protocol. We combine several techniques that we already know, hardware or software, in order to improve the security of the system we have, or to produce a novel mechanism. It's usually a battle between the attackers and the defenders, and the benefit from investing in security is not profound until we have an incident. So let's see, what is the actual current landscape? What is the typical system? So a typical system, if we want to see it in a holistic overview of the system, we have to think of security in several layers. We have decided to split the security in 7 different layers. We have seen also some other ways of splitting the security in 4 or 3 layers. So based on our view, we have the user-centric security. So how we can deal with the security of the user that somehow reacts and acts on our systems. This can be the end user or the administrator with some privileged rights and access control. We have also the applications. So here we talk about data-centric security. What are different applications we have now inside our systems? Whom have we bought these applications from, or have we created in-house? How secure they are, etc. Then we move to the system software-centric security. So here we have the different application or operating systems that we use. Every operating system has different pros and cons. Another layer is the network-centric security. The network-centric security, here we have to deal with how the packets are exchanged inside the network. If we have if we use any honeywords, how we do air gapping, how we use the firewalls and other solutions in order to secure the network. And of course, we have the device-centric security. Here we have to have in our mind that different entities cannot accommodate the same solutions. For example, if we have a smart camera, we have to think of lightweight protocols, lightweight solutions, as compared to a smart car, which is a system on itself, when we can actually apply more complex solutions. So in general, we have a complex interconnected systems that they one affect the other, highly heterogeneous devices and environments that we need our solutions to be able to be applied, highly dynamic environments, different entities come and go, not only nodes, but also people that react with the system. And also we have highly mobile devices inside this environment. The dynamic environment is something we have seen also during the COVID era. We have seen that there is no, as we say, there is no border of the company, of the system anymore. Many people work from home, so we cannot easily secure their organization. Now, for the first solution, which we talk about authentication, one of the major solutions we used to have for several years is the password. So we use some username and passwords in order to be able to authenticate it in the system and access whatever we have right to access inside the company. The typical username and password has a lot of security problems. That's why and a lot of years ago, the two-factor authentication and more factor authentication has been introduced. So what are the authentication mechanisms that we know, especially for mobile banking, for example, or other critical sectors? We have some ways of, except from the username and the password, to ask from the user to enter another one-time password that is sent to the user through the mobile phone by a text, or it is created through a hardware token. Of course, all of these solutions have their own problems that we're going to see in the next slides. In general, how two-factor authentication works. We have the user who is asked by the program or by the website to log in. The users enter this platform by using a username and password. Okay, these are matched with the information that is stored inside the server, and if this information is correct, the user is allowed to move to the next step. Now the website, the application that runs behind the website, creates a one-time password which is sent to the user. This one-time password then is again entered in the platform, and if this is correct, then the user is given the full access inside the platform. Then we have two types of two-factor authentication products. We have the hardware and the software solutions, each of which has their own pros and cons. So in general, before having a person entering a system, that person must be trusted. So it must provide some information that is correct. This information can be plain text, can be voice, call, or mail, but nowadays we also have authenticator applications that can produce one-time passwords that can stay for 30 seconds or 12 or 20 or 10 seconds, depending on the security level we have, and the user must put this one-time password that's produced by authenticator to the platform. Okay. Another solution that used to be very well known some years ago was the hardware tokens. Using these hardware tokens, the user first had to enter the username and the password, then the hardware token was producing one-time password that was of many characters. Some characters was about the ID of the user, and some other it was the one-time password again that the user had to enter in order to access the platform. Another part that I wanted to show you, to talk about a bit, is the QR codes, which are used in information security for authenticating cryptography, e-voting verification, optical watermarking, data hiding, and secret sharing. So QR codes are used in several applications, in several fields. But also, we have seen that they can be combined with steganography. So we have image steganography system that combines hidden data, text data, and image data into a cover image. So the QR code is hidden inside the image that the user can use, can scan in order to enter the system. In typical, the QR codes have some information that can be, when written by the application, is just zeros and ones. So it's a correct password that can be used in order to access some application. Of course, inside the QR codes, there are also some correction, error correction part. So if there are one or two errors, this can be automatically corrected by using the error correction system that is embedded inside the QR codes. So moving from two-factor authentication, we have seen recently that a lot of multi-factor authentication mechanisms exist that include the biometrics. This biometric authentication is not something new. It goes back more than 20 years. And it uses some biometric characteristics that can be somehow mapped and translated into bits that can be used when the user wants to access again the system. The problem is that these biometric characteristics are not entirely confidential. Again, they can be stolen by some applications. For example, the fingerprint can be retrieved easily by Mac, and facial characteristics can be obtained from an image of a user, and that is why this biometric authentication is now more dynamic as compared to the static biometric authentication that used to exist several years ago. Also, another important thing that we need to think about it here is that we have seen some passwordless solutions that exist nowadays that propose that we forget about the password and we use biometric as the first factor authentication. So again, biometric characteristics are very important for the authentication to systems. So in order to authenticate, we have different biometric characteristics that we can use. So if you see in this slide, there are a lot of different solutions proposed that can use almost all of the characteristics of a person, even the way that they walk inside because every person walks in a different way. In general, we have the two-factor authentication that is something you know and something you have. Three-factor authentication, something you know, something you have, and something you are. Or multi-factor in general, something you know, something you have, something you are, someone you are, and others. Okay. So something you know is a password, something you have may be a smart card, and someone you are is a fingerprint or some biometric characteristic. Okay. In general, the biometric authentication starts with the detection of this biometric characteristic can be the iris, the segmentation, feature extraction, template selection, and matching the iris with the pattern that exists already for the user. Okay, so all this information in the end is just zeros and ones that must be in the correct order as the order that is for the user when registered. Now, what are the security issues of two-factor authentication proposed mechanisms? There are a lot of limitations for two-factor authentication. For example, for hardware tokens, it's the cost of purchasing, issuing, and handling the tokens. If you have a lot of different systems that each one demands a different token, then how you store them, maybe you misplace them, or these can be stolen. So this second factor is lost. Also, you have here a threat to the supply chain, which is something that is now a very important threat. So you have to trust security of the issuer or manufacturer of the hardware. Another problem with the security is some other procedures that exist, like account recovery, password recovery, which can be used by the hackers in order to bypass the security of the systems. Okay, we have some instances we have seen tokens being stolen. We have instances we have seen brute forcing and other attacks that can bypass the two-factor authentication. In general, we have seen that two-factor authentication relies on simple text messages that are unencrypted or authenticators that again can be bypassed if the mobile phone is somehow infected by a malware. Now we have some single infection attacks. For example, here we see the entropy of the runtime passwords produced by Dropbox, Google, and Twitter. It was a research that being conducted in 2014 by these researchers. And we have seen, you see here that the entropy of Google is not as good as Dropbox and Twitter, which can be used by the hackers in order to predict the next one-time passwords. Other procedures that can be used in order to bypass the two-factor authentication is two-factor authentication deactivation procedure, recovery mechanisms, and of course, one important aspect is how these one-time passwords are generated by which procedure and how easy it is for this procedure to be replayed by a hacker. Of course, we have some more complex attacks like dual infection attacks. So here we have an example. We have the primary infection. Someone can attack the computer and also can, on the same time, the same hacker, for example, or another hacker can have a malware inside the mobile phone. So here, the attacker can steal the password when entered by the mobile in the desktop, and also can steal the one-time password that is sent to the mobile phone, and that thus can authenticate to the system. This, of course, is a very complex scenario. Another part that can be used in order to bypass the two-factor authentication is SIM cloning. We have seen several incidents recently with SIM cloning. So once the SIM is cloned, all the text, two-factor, the one-time passwords that are sent to your mobile phone are sent to the other mobile phone who has this cloned SIM. So if the attacker already knows the password, can also use the one-time password in order to enter the system. Also, in general social engineering, someone that has a target of a person can use the social engineering, collect all information about work activities and personal activities in order to send to the victim a personal message that looks legitimate but includes an infected file that can infect either the desktop or the mobile phone in order to do in order to put the virus inside in order to steal all the one-time passwords and the password from the first factor. Here is a data breach that was revealed early the previous year, which was somehow connected to a SIM shopping attack. And due to this SIM shopping attack, attackers managed to steal personal identification number and other information from the users and do some transactions online in order to steal some money from the user or buy some goods using his or her money. Okay. So the last part that I need to introduce to you in order for you to be able to understand how the novel system works is Honeyword. This is again an old solution that is used mainly for databases. So when you register in one system, you have your username, and also you have your password, which you decide which password it is, and it is stored inside the database after being hashed and salted. Okay, so you have one username and one password. Since there were a lot of data breaches that all this information was stolen, and the attacker could do some dictionary attack or brute force attack in order to find which was the password that producing the same hash value, some scholars have proposed the use of honeywords. So instead of only storing one username and one password, also some fake passwords are stored and linked to the same account in order, if someone managed to take the database outside of the company, do this data breach, not to be able to know which of these passwords are the correct. For example, imagine we have one user with 10 different passwords. Only one is the correct, which is called the correct password, and the others are the honeywords. Okay. So if the attacker managed to steal the database and do some dictionary attack and find out what are the correct passwords, then he doesn't know which of these is the correct. If the attacker tries to enter the system and put the username and one of the fake passwords, then the account is locked and the IT is informed that there was a data breach or something that needs to be investigated further. Okay? So this is the idea of honeywords. So having in mind that two-factor authentication is a very good solution, but has a lot of drawbacks, especially when you use biometrics, which is a bit more sophisticated. It cannot be used for every mobile device yet. We have decided to create a new mechanism that's called two-factor honeytoken authentication mechanism. So in this solution, during the registration of the user, except from the information that puts aside and chooses a password, whatever, he has also to pick one number from 1 to n, depending on what is the capability of the system. So, so let's imagine that the user enters the system, puts the information, and chooses the number 1. Okay, out of n. We don't care what is the n. For this prototype, we have n as 3. So we will produce 3 one-time passwords. Okay, so the user enters, registers to the system and chooses number 1. Once he tries to log in later in the system, he puts username and the password, and then he receives a text message to his mobile phone with 3 one-time passwords. One-time password 2, and one-time password 3. Or one-time password, one-time password, one-time password, doesn't matter. 3 different numbers in one single message. Only the user knows which of these 3 one-time passwords is the correct, because he has chosen the respective number, 1, 2, or 3. For this user, only the first one is the correct and the others are fake. So imagine that the hacker has access to the mobile phone, can read the messages somehow, and he also knows the password of the user. So he can pass the first stage, username password, but he cannot pass the second stage because he doesn't know which one-time password is the correct. So here is something between 2-factor and 3-factor authentication, but it's something you know, something you have, and something you know again. So it's something novel according to our knowledge. Okay. So here is some slides of the code and how it looks like. And of course, instead of using the one-time password taken out of the message, we can also scan one of these QR codes in order to retrieve the same one-time password. Again, the one QR code is the correct and the other 2 are fake. But they are all produced in a legitimate way from the same random generator procedure, okay? So they all look legitimate, but only one of these is the correct. I'm going to show you some demos later. So what are we now investigated in this mechanism? We try to see what is the distance among the one-time passwords. We try to see how we can create or use novel pseudo-random generators. We have tried to embed 2-factor authenticators, to embed our solution to authenticators. We have managed to embed it to Google Authenticator already. And also, maybe we're going to see in the future how we can provide this 2-factor authentication as a service for any website or application that wants to use it for securing further the system. Also, one important aspect we need to have in our mind, how we can secure the registration process or the other side processes like deactivation or password restoration, etc., which can be used by the hackers in order to bypass the security. So in order to find the distance between one-time passwords, in order to avoid having one-time passwords that are very similar the one to the other, and by a mistake, the user put one of the fakes, passwords, we use the Hamming distance between the one-time passwords in order to have a distance big enough in order to avoid such problems. For randomness, we know the importance of randomness that is used in any aspect of cryptography, like session keys, public key generations, key streaming of one-time pad, etc. And how important it is for all the encryption mechanisms like DES, RSA, etc. And for that, we know that for now we are using a pseudo-random generator. That actually, what does it do? It expands a short random string to a long string that appears to be random, but although it's fast and secure, it is not truly random because there is one initial seed that is not so probabilistic as we wish it would be. So in general, randomness is important because we want to have an unpredictable series of one-time passwords, and this can be done if we have a uniform distribution of ones and zeros, and you have independence between the one-time password produced and the previous one-time passwords. So unpredictability is very important in order to have statistically independent one-time passwords that are produced. This cannot be done from the typical generator we have, which can be random, pseudo-random generators, etc. But we have seen some recent works that use thermal noise or radioactive decay, so some physical measures, natural phenomena as a sources in order to create this true random generator, to produce through true random generator the one-time passwords. In general, a good true random generator must have a good entropy in source, a good harvesting mechanism that cannot disturb the physical process, and a good post-processing mechanism in order to provide tolerance when we have some environmental tampering. Okay, in general, we have three types of authenticators: the time-based one-time password, where we have the same secret to the user and the server, and this can be used in order to do some hashing and do some matching of the information that is produced. But what about the secret, and what about the registration step if using these authenticators? These are two vulnerable parts of this authenticator. Another part of the authenticator we can use is the HMAC-based one-time algorithm that use the secret key and the moving factor that are combined in order to create the one-time password. And this one-time password is valid until it's used or until a subsequent one is validated by the server, which again has some vulnerabilities that can be exploited by the hackers. What is now mainly used is the universal second factor authenticators, when we have the user's private key, which is used in order to sign a challenge that is produced by the server, which is sent to the server in order to verify using the public key of the user that is the legitimate user that produced this challenge, that signed the challenge. So the important thing here is how securely stored is the private key in the user device. We have seen also recently some authentication as a service, some cloud-based authenticators that can do all of this fancy thing with authenticator, but in the end, all this information is encrypted and stored and protected by a user-defined password, only a user-defined password. So all this security falls and fails according to our viewing, since it is now there is a single point of failure of a user-defined password that is securing all this procedure. So again, we have the same problem. This is a screenshot of the registration phase of our novel two-factor honeytoken authentication mechanism and how the user picks one of these numbers. And we have also two videos. This is the video with the texts and the registration phase. No sound for this video, and we have another one with the Google Authenticator. So now the user receives these 3 OTP numbers. If he enters the correct OTP number, then he can enter the system. If he puts the wrong OTP number, then depending on the instant response plans we have in place, we can deactivate the account, inform the user that maybe there is a hack, or inform the bank or the application that maybe this user has an issue, or whatever other countermeasures we want to have in place. Okay, so this is the first video. I have another one with a Google Authenticator. What's the difference here? So here the procedure is the same, but during registration there are 3 QR codes that are scanned by the mobile device of the user, and the user creates 3 accounts for the same application, and all these accounts produce legitimate one-time passwords every 30 seconds, but only one of these is the legitimate one and the other are fake. Okay. So again, if someone has access or can view what we see in our mobile phone, he or she doesn't know which of the 3 QR codes is the correct. All the three passwords produced by Authenticator are the correct. Okay. So this is the first part, our 2-factor honeytoken authentication mechanism. We have published parts of this solution already in conferences, and we are now in the procedure of moving from a prototype to a more professional, let's say, solution that we can apply to real infrastructures. Okay. We also have a demo. We also have a website that we can share with you if you want to test it on your own at your time, and also send us a feedback. Okay, so the second part is the SNIS application. This came out of the need for actually securing the information that is exchanged between different users. In general, now mobile phones is not as they used to be, only for texting and calling, but is something that we use it in. We have a variety of software applications that will exchange voice, text, email, video, and information with many social, using many social networks. So the social media applications is the correct one. Okay, but since we install a lot of different applications on our mobile phone, we are not sure whether these are correct, legitimate, uninfected, etc. So a lot of malware can be installed in our computer. This is actually a very serious problem. Imagine that there are different categorization of the malware, like banking malware that collects bank login and your password details, ransomware, you all probably know about it, SMS Trojans, send text message to pre-enumerate numbers and this, to spread around, spyware that can monitor online activity, record information, track your location. So this can be combined with other modes, with other data in order to reveal some of your sensitive data. So we have a lot of current end-to-end, as they are called, solutions, but these are neglecting the human factor. So data, as from the new message applications, are encrypted during transmission, but are not encrypted in the end node. So in your mobile phone and the mobile phone of the other user, all the information is unencrypted. Okay. So in general, we create and consume data in clear text on those devices. But as we said, these mobile devices are vulnerable to malware and also to eavesdropping. It can be physical or digital. Why? Because we have a lot of applications that install the mobile devices which are not secure. Okay. One part of this malware is called stalkerware, and this can be used in order to read information by malicious actors. So stalkerware is another definition of spyware, and is used to spy other partners. Okay, so this is called in general intimate partner stalking. Uses stalkerware. It's a growing problem. In the UK, one of the 10 people in the relationship admit to using this stalkerware, read text and listen messages and emails, monitor social media activity, listen and record phone calls, access photo, etc. Okay, so the mobile phone is not so secure anymore. So here are some other statistics. 5% of adults have used stalkerware. 2 in 5 adults in the UK think that the pattern might likely to install in this kind of thing. So this is something that is growing not only in the UK and also in the USA, etc. So what are the primary research goals of our solution? We try to extend the end-to-end encryption to the end nodes. Okay. So for that, we will use innovative hardware and software technologies in order to be robust against such kind of attacks. So we're going to incorporate, we have already done it in our prototype, additional level of encryption techniques to enhance privacy, and also we're going to enhance security using our multi-factor authentication mechanism. So in general, this solution must be user-friendly, introduce minimal delay in message transmission and delivery, so we don't want to have a lot of delay. It can be used in any platform, in any Android or other kind of operating system used. We also incorporate multi-factor authentication, and we try to decouple privacy from a mobile device using hardware and software technologies. So we think that this mobile device we have as a phone is not secure, and we try to move security out of this mobile phone. We plan the future also to incorporate augmented reality inside this system with some smart glasses. I'm going to show you some example of what are the future plans. So in general, the hardware and software solution that we are building encrypts data before being transmitted. Okay, and this device can be either a smart glass solution or a smart screen overlay on top of your mobile phone, or any other hardware or software that can be linked, installed, or connected to your device. For that, we're using a pair of public-private key for every user, okay, and the mechanism encrypts data on the new device before being sent to your mobile phone. So this is the first prototype. So we have a Raspberry Pi, and we have an external LSD screen, and we have also a reader, an RFID, a fingerprint reader, and RFID reader that can be used in order to authenticate the user. So in general, the SNIS application starts how we create a message. The SNIS application starts, and the SMS email is selected that needs to be sent. Okay. The fingerprint is used to verify the user, and the external hardware software is used to create the message, so that the message is not created inside the mobile phone. Okay, it is created in the separate device. In the video I'm going to show you later, the separate device is another mobile phone, but we are also building the same prototype in a Raspberry Pi, and in the future we're going to build it in a more sophisticated hardware. Okay, so the SNIS encrypts the clear text into ciphertext. This is passed to your mobile phone, which through the messaging application that we want to use, it is sent and double encrypted by this mechanism before being sent to the other user. Okay. So the other user receives this message. The SNIS application starts again, decrypts the ciphertext into the SNIS ciphertext because we have double encryption. Okay, and then this is sent to the other hardware device when we authenticate the user and we decrypt the message which is shown to the user. This other hardware device, as said, can be any device that you have in your mind, like an overlay screen or smart glasses or whatever. These are some of the ideas we have for the future. So in general, we have the SNIS application management service, sender mobile message application view, encryption via the SNIS application, and then message application, double encryption of the message before being sent and received and retrieved by the end user. So we have general three ideas. One is a pure software application for Android mobile phones, which is mainly for demonstrating purposes and also for us to see that everything can actually work. Because again, we have a software application. If the Android mobile or mobile device is infected, this is not secure. Then we have our hardware prototype using a Raspberry Pi, and also have a hardware prototype using a second mobile phone that is secure because we don't have anything else installed there. And the final target is to integrate this into smart glasses developer kit that we aim to use. So how is our prototype working? So we have the user that has the mobile phone on the right hand. Let me show you. So this is the mobile phone of the user, and this is the second hardware that is used. Okay, we have biometric authentication in order to the user to access the mobile phone, and we have these are connected through Bluetooth. These two devices. Okay, and when connected, they can be used in order to exchange, to create a message and forward it to the other user. Okay, the other user also has two devices, the mobile device with all the applications, the infected mobile device, let's say, and the secure hardware that's used only for decrypting the messages that are sent to the end user. Okay. So this is the demo that is with sound.
Sorry to interrupt, Professor. Is there supposed to be a sound in this?
Tell me again.
Is there supposed to be a sound in this?
Yes. You cannot hear it?
No, we can't hear the sound.
I can hear the sound. I don't know why you cannot.
We can see the video, but we can't hear.
It's fine.
Yeah.
I will also say the link to the video for
Sure.
everyone. Or maybe maybe it's the microphone. It doesn't pick such a.
That's fine. I think we can see anyways.
Yeah. So every user has two mobile phones. One is connected to the internet in order to exchange messages with the other user, and the other is connected through Bluetooth, which is the external device that does the encryption and decryption using this pair of public-private key for every user, and uses the Diffie-Hellman protocol. Okay. So here we can see how the application works without the added layer of security. But now we are going to use the sneeze encryption on top of the plain text. we haven't automated this procedure yet. So we have the internet chat and the Bluetooth chat, and we have to copy paste the encrypted message from one chat to the other, which we will automate in the future. Okay. So this is the by Nithis. So what are the impact, the positive impact, the beneficiaries? We see as impact as beneficiaries any employees that work in critical sectors and need some other layer of security. All the users in general that can be secured against malware, eavesdropping attacks, and so on. And of course, the military and police will need highly secure communication channel for both voice and text information. So these are the references. For the first part, these are the publications we have already done. And for the second part, these are the publications for the SNIS. So we have two publications for the two-factor authentication and two publications for the SNIS. Unfortunately, you couldn't hear the voice, the sound on this video, but I will share it with you online in order for all of you to be able to access it later. So, thank you all.
Thank you so much, Professor Lindros. That was really nice. Let me see if we have any questions. All right, I have some. I see some question. That's from Abimbola. He says, what type of encryption does SNIS use?
Yeah. We have RSA.
Sorry?
RSA encryption we are using. Okay. And regarding the power consumption, we haven't done any study on that, if there is a power consumption rate. Maybe this is in order to use it to understand if there is a malware or a power consumption rate for our application. If there is any power consumption from our application. We haven't done any study for that yet. Yeah.
Thank you so much. I have a question myself. When we were talking about the 2FHA authentication, you mentioned that the user selects a number out of n number. I think some number you select between that. How is it always a fixed number? So during registration, you showed us the demo for that as well, where the user is selecting during registration a number, I suppose, if I got that correct. Is that fixed while registration, and it is not dynamic every time the user is logging in? Once selected, it's done.
Yeah. During registration, you pick one number. You say that for my account, I want only, for example, the second one-time password to be correct and the other to be fake. Okay? And this, from this time onwards, anytime you log in, you receive a number of one-time passwords and only the second is the correct. If you want later, the later stage, to enter the platform and change this number to another number, it's fine, you can do it. So later you can say, okay, from now on, I want the fourth one to be the correct one.
Okay. And who decides the maximum number? That n number is decided by the software?
No, it has to do with the capability of the application. So what is the only problem? Imagine that for every user, every time that the user logins, you create a one-time password. Now you create a number of one-time passwords. So you need a stronger machine, a true random generator engine that produces these numbers. This is normally a server that does all this job.
Yeah.
So if you want for every user to have 5 one-time passwords, it's like having 5 times more users. Okay, so you need to have more hardware to produce this one-time password. That's the only issue. There's no other burden.
Yeah, that's
only this. Yeah.
Yeah, and another thing, in your other demo, when you were putting in the user number, it was excuse me, it was coming as dotted like a password. Was there significance to it? Because in a username, when you were putting in, which did not have a sound, that username, when you were putting, those were dotted. So it's like hidden username. So I wasn't sure whether it was intentional or why would the
No,
username be dotted?
no, it's just for the first user, we saw also the registration phase. So there
Yeah.
was no username. And then he wrote down his username. So there's not dotted, it was just the registration phase.
Yeah, in the registration page. Yeah.
It would be more clear anyway if you had the sound. Unfortunately, I don't know how the sound didn't pass from the microphone because it has sound. It was unfortunate. Okay.
That's fine. And also, is there a way to retrieve the OTP number once you've forgotten? In case you forget the OTP number, what you had selected, what would one do?
You can go to the registration again phase and see what is the number you have picked. Okay, so again, this is the problem. If this registration phase is not very secure, then again someone could retrieve all this information.
All right.
So there are some other procedures you can go and reactivate all this, start all this procedure again.
Okay, that's
happens
good.
with all the systems. Yeah.
All right, and the sneak part was really good. That was something nice. Well, the stalking bit, I understood. The only thing I wanted to know, with the, obviously it's in a prototype stage, like you mentioned, that you had to copy from there. It will improve as you go further. But could one choose what messages to encrypt and what not to encrypt? In the sense, if I'm just talking to my daughter, I don't want to go through the whole process of encryption. It's only when I am doing some dubious job that I would like it to be encrypted.
Yeah, I understand. Yes, in the final product, this will not be an issue. It will be very easy. But for now, since, as you've seen, it's not automated at all. So you write a message, you have to copy paste it to the other chatting mechanism, the encrypted message to be sent to the other device. But if you want some message to be encrypted, even now you can do it. We have shown you that you can send unencrypted messages. But I think this is a very good proposal also to make such a distinction between encrypted and maybe press a button and say from now on I want everything to be encrypted, and now to close it, turn it off, something like that. Yeah.
The only giveaway in that would be if I'm encrypting certain messages, it gives away that I'm doing something wrong there. If somebody is stalking me, they will still get to know something is wrong with that encryption if I'm using, and I'm not using for other things.
Yeah.
So that is something there. But I think we have another one. Given the layered approach to authentication, how much overhead does it introduce?
For the first solution, probably. Yeah, there is no overhead. As we said, the only overhead is for the hardware that needs to produce the one-time passwords. So it doesn't change the business. It doesn't change the interaction of the user with the platform at all. You just receive a message with several OTPs. You just have to remember one number. That's all. And for also for the application that produces the one-time password, is not such a big overhead. You just need to buy a bigger hardware, a bigger server that produces the one-time passwords. That's all. Or you can use software to produce the one-time passwords, but it's not so secure. That's all. So the overhead is not too much.
Thank you so much. I think we are okay with the questions. I don't see any more coming. Thank you so much, Professor. And it was lovely to see the work that you're doing, and it was nice hearing about it. Thank you so much. I think we can stop the session now. Thank you. And thank you, audience, for coming.
Thank you for inviting me. Thank you very much.